Welcome back, mathematicians. Today we guys are going to go over section 1.5, and that's all about exponential functions. So I thought it'd be fun if we started out with a math fact. Did you know that you cannot fold a piece of paper more than 8 times? If you could, fold it as many times as you wanted, it would only take 42 folds to reach the moon. Well, what does this have to do with exponential functions? Let's call P the thickness of the paper. So if I don't fold it at all, it's just P. After one fold, if I fold it over itself once, I'm going to have 2P. If I fold it in half again, I'll get 2 times 2P, just 4P. What about if I fold it 3 times? I'll get 2 times 4P, which is 2 times 2 times 2, 2 to the third P, which is 8P. What if I keep folding it X amount of times? I get 2 to the X P. In math, we call y equal to 2 to the x an exponential function. Because our variable x is in the exponent. In general, we can write an exponential function with base 10, sorry, not base 10, base A, where A is some positive number, as f of x equal to a to the x. You're like, cool, when am I ever going to use this? You actually encounter exponential functions every day. So what do I mean by that? Well, let's say in 2014, you got gifted $100. You decide to invest that $100 into a savings account. Maybe if I wrote English. To invest. So the saving account has a few properties. It has interest compounded annually. So that means once a year. At a rate of 5.5%. All right. Let's assume you invested all $100 and never withdrew or added more. How can we write a function to describe the amount of money in your bank account? After, let's say, X years. All right. So let's call your principal balance, whatever you start with, P. We'll call that 100. Well, after 1 year, since it's compounded annually, so I'm going to have my original 100 in there, P, plus I'm going to get 5.5% of that. So 5.5% is 5.5 divided by 100. Well, we can see I can not just adding 5.5%, it's percent of what? Of the balance that I have in my account. That guy right there. So, well, each term has a P in it. So let me pull out a P. I pull out this first one, it leaves me with 1 plus 5.5 divided by 100 is 0.55. That decimal needs to be moved over. 0.055, yeah, P. So that's how much we have after 1 year. Well, after year 2, I'm going to start with 1.055 P plus I'm going to have 5% of that amount. So I'm going to have 5. Let's quickly just make that 0.055 times 1.055 P. Well, each term now has a 1.055 in it, so I can pull that out. and I'm left with 1 plus 0.055 times 1.055 p. Simplify it again. 1.055, 1.055 p. One more time. Those two things are just the same thing multiplied together, so I can make it 1.055 squared times p. If you see a pattern, this is after 1 year, I have 1.055 to the first power p. After the second year, I have 1.055 to the 2p. So after year x, we'll have a equal to 1.055 to the x power times p. Since p was 100, I can write it as 1.055 x times 100. All right. Since x is in the exponent, that's an exponential function. So compounding interest annually we can write a general function. We're going to have a equal to our starting value, p, our starting investment, 1 plus r to the x. So p is our initial investment. R is your interest rate as a decimal. So as you can see, we're probably going to be, hopefully, right, interest is going to make our account grow. That would be kind of silly if the bank charged us money. So let's review a few more exponential rules and properties before we move on. Let's put new color. I like this green. So a few straightforward ones. If n is a positive number, and y equals a to the x, when x equals x to the negative n, we'll have y equal a to the negative n, and I can rewrite that as 1 over a to the n. And then I actually can do something really cool. I can pull out this n. I can do that because 1 to the n is 1. So these three things are equal to n. All right. When x equals 1 divided by n, we'll have y equal to a to the 1 divided by n, and that's the same as a to the nth root. So if it was 1 over 2, it would be a square root. All right? So if p and q are positive numbers, and x equals p divided by q, we'll have y equal to a p divided by q. And I can rewrite that as a to the p of the qth root, or a to the qth root to the p. All right, those are all the same. So the main 6 exponential rules that are not 6, 5 that are really important are these. So first we're going to let a be greater than 0 and b be greater than 0. All right, and x and y are just going to be real numbers. We can say that they are in the reals. That's what that double bar R is. So first one is that a to the x times a to the y equals a to the x plus y. So if the bases are the same and they're being multiplied, their exponents are going to add. What if we had a to the x divided by a to the y? Well, that equals a to the x minus y. Kind of what we saw up here. If I have something, an exponent in the denominator, I can rewrite it in the numerator with a negative exponent. And that's how I get rule 2. Rule 3 tells me if I have a to the x and then to the y again, I have a to the x times y. Alrighty. Fourth rule, I have a to the x times b to the x. So now my bases aren't the same, but my exponents are. I can collect that exponent, so I'll have a times b, that whole thing to the x. And then our last one, if I have a to the x over b to the x, I can pull out that x and I get a divided by b, the whole thing to the x. Alrighty? These are very important. You'll use them a lot this semester, so I highly suggest jotting them down. So let's do a few examples. So 1.516, we're asked to simplify these problems. So this one is we're going to simplify the expression 13 to the square root of 2, this whole thing to the square root of 2 divided by 2. Okay? Well, I can use rule 3. So that 13, here, let's write this. 13 to the square root of 2, square root of 2 divided by 2 equals 13 square root of 2 times the square root of 2 divided by 2. Square root of 2 times the square root of 2 is just 2. So I have 13, 2 divided by 2. Well, 2 divided by 2 is just 1, so I'm just left with 13. Great. One of my favorite ones is 1.5.11. Again, we're simplifying the expression. And we're given 16 squared times 16 to the negative 1.75. Well, those two things have the same basis and two different exponents, so let's use rule 1. So I'm going to take 16, 2 times 16 to the negative 1, 1. Negative 1.75. So I'll have 16 to the 2 minus 1.75, which is 16 to the 0.25. Well, I think I can simplify this a little bit more. So, I know I can rewrite 16 as 2 to the what? 2 to the 4th, right? So I can write 16 to the 0.25 as 2 to the 4th to the 0.25. I'm going to again use rule 3. So then I can multiply 4 times 0.25. So I'll have 2, 4 times 0.25. Well, 4 times a quarter is just 1. So I just get 2. I'm not saying 16 to the 0.25 is wrong. I just can simplify it to just 2, which is a lot more simple. All right. So we have a favorite exponential function. Whoa, chill. We call it the natural function. No, sorry, natural exponential function. Just the natural function. All right, that is y equals e to the x. E is some constant, 2.718281, something with more 2's and 8's going on. I am not going to explain how we get E. That is later on in life. But this is, E is just a number. If you see E in a function, it's just a number. It's not another variable. Okay? So then, why is E so important and what do we like about it? If I draw you a rough graph of E, then when it crosses the x-axis, the slope is actually going to be 1. Slope of the graph is 1. So what does that look like? We're going to be coming up here and then boom, like that. So this is the y-axis. So right here, act like that's a slope of 1. E to the x also has some really interesting properties when we get to derivatives and its inverse. All right, so let's talk about something more fun than e to the x and when we can use it. Exponential growth and decay. We kind of already talked about growth, right? Our interest rate growing, but we can also talk about things decaying. Radiation, the size of a tumor, the number of sick people, hopefully decays, and things like that. So we can let k be a constant. In exponential growth, expo, it's not how you spell that word, there we go, exponential growth. We'll have y equals y naught e to the kt, where k is a positive number. Oh yeah, k can't be 0. That would just be silly. Y naught is our initial value, our initial investment, our number of people in a city, the size of something, just our initial value. Usually if something has a little 0 like that, you say y naught. Alrighty, so exponential decay looks a little similar. Y equals y naught e to the kt, but now k is negative, less than 0. All right, so we saw how we could be compounding our interest annually, but what if we compound interest continuously? So how did I draw this up here? Did I have a cute little thing for it? Yeah, I did. Okay. How do you compound interest continuously? Every second, every millisecond? How do you measure that? Well, we use it using this function, which I think you guys might be familiar with. So we usually see it as A equals PE to the RT, apert, or Y equal to PE to the RT. P is our starting investment. Money, just starting value, basically. R is the rate in decimals. You're usually given it in percentage. You just need to divide it by 100, and that's how you can get it into a decimal. Alrighty. So let's do some fun examples. of when to use these functions. So in 1.530, the population in some city called Silver Run in the year 1890 was 6,250. We're going to assume the population increased at a constant rate of 0.25% a year. We are then asked to estimate the population in 1915 and 1940. So let's first make an equation, right? So population, it's increasing. So increasing implies we're going to use what? Exponential growth. All right, so then we have some unknowns. I need to know what my initial value is and my R is. So we're told that in 1890, we'll call that time 0. Y naught is going to be 6250, and my R is going to be 2.75%. All right. So now I have an equation of y equals 6250 e to the 0.0275 t. We're using t right here instead of x. It's just a variable. It's usually used with time. So in 1915, what's t? Well, if I made 1890 times 0, t is going to equal 1915 minus 1890, which is 25, right? So we're looking at t equals 25. And in 1940, t will equal 50. So when t equals 25, we're going to have y equal to 6250 e to the 0.025 times 25. If you plug that into your handy dandy calculator, you're going to get 12,429.6 people. If you want to round this up to 30 instead of 29, totally acceptable. You can't have 0.6 of a person. When t equals 50, let's do the same thing, right? Y equals 6250 e to the 0.02550, right? 50. going to put that in my handy dandy calculator. And I'm going to get 24,719.23 people. It's really good to put the units when you are in a real life example, right? They're telling me it's population, so my units is people. Alrighty. So what if I'm not given an initial value? We're not going to do part B for this problem because I don't really like it. So let's look at $1.533. All right. So we're asked to determine how much time it takes to double our investment. We have an interest rate of 6.25%. And we are compounded annually, not continuously, annually. So if you remember that equation, it is A equal to P1 plus R to the T, or X. Let's keep with X. All right, so P, we don't know. Well, I do know R. So I know R is 6.25%. So I'm dividing by that 100 so that I can get a decimal. Well, I actually don't need to know what P is because I want to know how long it takes to double our investment. So if our initial is P, when we double it, we'll have 2P in our account. So I'll have 2P equal to P, 1 plus 0.0625 to the X. Well, I can divide a P on both sides. So that I'll get 2 equal to 1.0625 to the T. How would you solve for T? I can plug in some numbers into my calculator to kind of get what maybe two whole numbers it would be in between and check like that. So we could check and guess. We'll actually learn in section 1.6 right after this how to solve this. So we are done with 1.5 today.